Okie dokie. Well, let's look at section 1.4. This is this idea of continuity. And continuity, for the most part, for things we're dealing with, is pretty intuitive. So there's a curve f of x, and often what we say is, hey, it's continuous if we can draw the curve without ever picking up our pencil, something like that. And again, for intuition, that's pretty good. It does fall apart a little bit in some weird cases, but but again, that's a reasonable sort of thing. For continuity, it's at a point, so f of x is continuous at c. Okay, so that's x equals c. I could probably fit that in here, x equals c. Well, we need three things. One is the function better exists there, so f of c exists. But then also, if you think intuitively up here of, I'm coming along here to some, x equals c here, and if I'm not going to pick up my pencil, coming in this direction, if that's not getting picked up, then the road, so to speak, the path of f of x better go to f of c, and so that is our limit as x goes to c of f of x exists. And then finally, those two things have to be equal. So f of c has to equal the limit as x goes to c of f of x. And so we have those three things. Now, actually, in a lot of ways, this third statement, if that statement makes sense, then the first two statements had to be true anyway. I can't talk about f of c being equal to the limit as x goes to c of f of x if either f of c doesn't exist or the limit doesn't exist. So that's what's got to go there. Now, for the most part, our nice functions, our nice usual functions are continuous where we can evaluate them. Now we have a little bit of a caveat there. So this is on open intervals. Because we'll have to, in the next video, we'll introduce the one-sided limits and so forth. But so, when I look at things like polynomials, rational functions, trig functions, exponentials, power functions, right, powers, etc. You know, I'm sure I'm leaving something out, but the typical things that we deal with, they're all fine. You know, so let's take something that can have problems. Let's look at something like f of x equals 1 over x. So I can either call this a rational function or a power function, right? Because it's a one polynomial, the constant polynomial, over another very simple polynomial. So that's a rational function. But it could also be written as x to the negative 1, which is a power function. So if you look at that, and I look on any sort of open interval, an open interval is just an interval, you know, like 1, 2, like that. That's the open interval, and so that means all numbers between 1 and 2. That's not a coordinate. This is an interval. Looks a lot like a coordinate, but it's the interval on the x-axis from 1 to 2, but it doesn't include the endpoints. That's the idea of an open interval. Then, you know, if 1 over x is defined everywhere in that open interval, it's going to be continuous everywhere in that open interval. You know, so, you know, at 1.5 at 1.287654893, you know, something like that. At the square root of 2, that's inside there. F of x is you know, as long as it's defined everywhere in there, it's continuous everywhere in there. The only problem we have with f of x, right, is f of 0 is undefined. And so that's where we're going to have a discontinuity. Oops. Discontinuity because, well, we don't have this part number 1. And actually the limit doesn't exist there either, but so we're just way out of luck. But generally speaking, right, at nice points, everything's fine. You know, another one that can cause some problems is suppose you know, I've got something like that. Well, again, on an interval like 1/2 to 6, you know, that open interval, everything's fine, right? This is, I'll put fine up there, and everything's fine here, right? Not a problem. But at 0, the function's defined, but we have an issue with a two-sided limit there because I can't take the square root of a negative number. Okay, so the limit as x goes to 0 of the square root of x is undefined. Okay, now, again, in this section we talk about one-sided limits, and so we'll learn what to do about this. But you know, right now, right, a limit has to come in from both sides, and so that's undefined. So we would have a problem at 0, even though f of 0 exists. Okay. Now, so, you know, with this definition, we're really looking at just a few basic cases visually, right? You know, what can happen for discontinuities? I'm going to actually, I guess, go to page 2. Oh, I just saw, I'm amazed that I wasn't messing things up because the touch thing was still enabled. But okay, so, you know, discontinuities. Oh, there we go. Wow. Okay. Discontinuities. There we go. Okay. Discontinuities. Some very obvious sorts of things are at asymptotes. So if I've got like a vertical asymptote here, maybe my function does something like that. So you could say, well, the limit as x goes to c here is infinity, but you see it means it's still undefined. So this is discontinuous there. So there's one type of discontinuity, something like that due to a vertical asymptote. Actually, when we get into defining derivatives and so forth, what we tend to have in these cases is something a little less obvious, right? So I put an open circle here at C. Now, I could put a dot somewhere here, I could do something like that, just to say that f of c is defined. But the problem is that the limit is never, if I put that open circle and then whether or not I define the function somewhere else, the limit is not going to be the same as the function. So the limit exists, but it won't be the same as the function. Now, in this case, when we just have a little hole like that, but the limit seems to be fine, we actually call this a removable discontinuity. Because if I were to define the function just right, I could fill that point in and everything would be fine. Well, I'll look at a case of that in probably another video, but so there's that picture. Now we could, similar to that, but again much more noticeable about a discontinuity, maybe there the function's defined, but we do something like that with our f of x, and so, well, the function's defined, but the limit doesn't exist, right? Because I get an answer coming in one direction that's different than an answer coming in the other direction. So those are all pretty typical. Now, a really weird one is C. So here's C. A weirder one where the limit doesn't exist is, something like we saw with a sine of 1 over x or something along those lines as x went to 0, is that if this thing, starts oscillating wildly, then again, the problem is f of c might be defined in here in this mess, but no limit exists. So it's really a limit issue. And of course back here, this could have been an open circle instead of that could have been an open circle instead of a closed circle. But there, if you notice that actually in 3 out of 4 of these cases, the problem, the real big issue is the limit doesn't exist. The limit doesn't exist here, and then these 2 cases, the limit doesn't exist. And because I could define f of c any way I want, but if the limit doesn't exist, I have a problem. Okay, here the limit exists, and so if I ended up defining f of c just the right way, I could end up making that a continuous function, in which case we would have, that's where we would have removed that discontinuity. Okay, so those are the kinds of things we're looking for. We're looking for them graphically. A lot of times we can use something like Desmos. Now you've got to be very, very careful with Desmos in this case. Okay, any technology graphing something, if it simply has a removable discontinuity, it will be very, very difficult to see, and so we also need to worry about some algebra. We'll call this video good. This is our introduction to our discontinuities and continuity. But again, basically something's continuous unless it's discontinuous. And so you tend to look for things where it's discontinuous, not so much where it's continuous.